So today we're going to talk about convergence analysis of the stochastic gradient descent algorithm. So here we are dealing with this stochastic programming problem. Right? So the objective function is the expected loss, where the expectation is taken over the data sample, C. Okay, so the randomness comes from this data. And we assume there's an underlying distribution, which we do not have access in many practical applications. Okay. So in SGD, the idea is that instead of computing the entire the gradient of the expected loss, we simply draw, in every iteration, we first draw a sample, like a set T from that distribution. We randomly draw a sample, or we collect a sample, and then compute the gradient of the loss function with regard to this particular sample. And we use this stochastic gradient to update the variable. And in particular, we assume that there are many schemes that can guarantee that such a stochastic gradient, although it is not exactly the full gradient, but in expectation, it is unbiased. The expectation of this stochastic gradient is exactly the full gradient of the original expected loss. And the convergence analysis is based on the several assumptions. So first of all, we assume the function is so let's consider the simplest case first. Well, the function is mu strongly convex L smooth. And we assume that this stochastic gradient that we use is an unbiased estimate of the full gradient. Okay. Basically, when we take expectation, so precisely when we take expectation of this GXT, okay. So this expectation usually, so it is taken over this CT. And it is given, the XT is given. So fix that model parameter, we take expectation with regard to this CT. This one is gradient f xt. So in expectation, the stochastic gradient gives the exact full gradient. But in practice, we use this as stochastic gradient instead of the expectation. So they are different. But on average, they are about the same. Okay, so this is the second assumption, unbiased assumption. The last assumption is to say that the second moment, roughly speaking, the second moment of the stochastic gradient is bounded by a constant plus the gradient norm. So the expectation of, so inside we have the stochastic gradient, and because the stochastic gradient is a norm, it's a vector, so we can consider the norm. We say take the norm to the power of 2. Take the norm to the power of 2. This is a random variable. If you view the norm of the gradient as a random variable, then this is the second moment of this random variable. Now, given x, so again, expectation is taken over c. So this is a conditional expectation, conditional x. This is less than equal to sigma g, a certain constant plus expectation plus another constant cg times the full gradient norm to the power of 2. So why do we want to control the second moment? Intuitively, we want, this is basically an assumption that on the finite variance of this stochastic gradient, because this part, the gradient of f is exactly, if we write it more explicitly, is the expected value of this g. Right. So this assumption says that the second moment is bounded by a constant plus the expected value to the power of 2. And we know for the variance of a random variable, the variance is the second moment subtracts the mean to the power of 2. Okay, so roughly speaking, this assumption provides a bound on the variance. Okay. For example, if this CG is 1, then you move this term to the left hand side. That is expectation of square subtracting the square of the expectation. Okay. That's roughly the variance of this stochastic gradient. Okay. So this assumption is essentially to say that the variance, intuitively, the variance is bounded variance. And if these assumptions can be justified for many examples in practice. So this is the main convergence result of the stochastic gradient descent for strongly convex problems. Right. So under these conditions, we have this result. So let's look at this result under the previous conditions. Suppose we choose this step size. Okay. We choose a constant step size, 1/L times Cg. Then we have the following convergence result. So this is like the function value gap. So the optimality gap in iteration t. And because this algorithm is randomized, algorithm is random. Right? If we go back to the algorithm, in every iteration, this Kasai T is a random sample collected from, for example, the underlying data distribution. So this Kasai T is random, which means the entire algorithm, this sequence of parameters xt is generated in a random process through the random process. Therefore, this algorithm, this xt, they are random variables. Their randomness depends on how we generate these T's. Okay. Therefore, in this convergence result, we care about the expected value of this optimality gap, because this fxt minus f star This is a random. XT is a random stuff. So we care about this. This is optimatic gap, but it's a random optimatic gap. So we care about the expected performance, the expected optimatic gap. Now this result says that the expected optimatic gap is roughly bounded by the right-hand side, which is the first term is a constant, depends on step size eta. And the second term is a geometrically diminishing term. So as t goes to infinity, the second term goes to 0. And you can see the convergence result is different from the other results that we have seen before. In this result, if we let t goes to infinity, if we run this SGD algorithm for many iterations, you can see that only the second term goes to 0. So this term goes to 0. The first term is a constant, only depends on the step size eta and some problem parameters. So it means that if we do this, then this algorithm, okay, it will converge, but only up to a constant error, up to this constant error. Therefore, at the very beginning, we have a very fast convergence, because intuitively at the very beginning, maybe the second term is very big. So the second term dominates, and then the second term decays geometrically fast. So we have a very fast decay, very fast convergence at the beginning. But once t becomes very big, the first term starts to dominate. Okay, and so eventually the convergence will slow down, and eventually it will be bottlenecked by this constant error. And in order to reduce this constant error, there are several scenarios. For example, we can let this L and mu, they are problem parameters, so they are guaranteed to be positive. So either this sigma g needs to be 0 or this eta needs to be very small. Right? So the first case is when this sigma g equals to 0, which means that, so go back to the definition of sigma g. This is where we introduce this sigma g. It means that the variance of the stochastic gradient is 0. Okay. If this estimate is very, which basically means that your stochastic gradient estimation is very accurate. So either this one is very small, so that the first term becomes very small. The convergence error can be very small. Or the other way is to make the step size very small. You can choose eta to be very close to the accuracy level that the desired accuracy level. But there's a trade-off. Once you choose a very small step size, the convergence error becomes very small. But on the other hand, the second term, it will converge very slowly. Okay? If you think about if eta is very small, that 1 minus eta mu is very close to 1. And that makes the that makes this coefficient decays slower. Okay, so there's a trade-off on this choice of step size. And this is a simulation example where we run SGD with a fixed step size. So you can see that so these three curves, red curve is running with 2 times alpha, so it's a relatively large step size. So alpha is a certain numerical number. Green curve is yeah. So you can see if we run with a large step size, eventually the algorithm will stop at a certain accuracy level. Right. So the bottom line is the minimum value. So there's a constant convergence error. But if we reduce the step size by 1 time, reduce from 2 alpha to alpha, then this green curve, it can converge to a lower, smaller convergence error. Okay. And if we further reduce the step size, the convergence error will be further reduced. So there's always this trade-off. Using a smaller step size, you can get eventually you will get a more accurate result. But on the other hand, using a large step size, you will more likely to have a faster convergence at the very beginning. So in practice, people usually do this use this strategy. Whenever the progress stalls, we will start to reduce the step size. Whenever you see this red curve starts to converge, so you are using a large step size at the very beginning, and at some point you see that the convergence becomes very slow, then you start to use this smaller step size. Okay. And after running SGD for some extra steps, once this green curve starts to slow down, you again reduce the step size and keep running the algorithm. Okay, so you have a decay in step size, and there are different strategies you can play to decay the step size. And we will look at this. This is another result that people usually use. Well, the setting is essentially the same. Okay, F is mu-Shannon convex, and assume the CG equals to 0. Okay, for simplicity. Now, the big difference is that here we are using a diminishing step size instead of using a constant step size. We let eta t in iteration t to be theta over t plus 1. Well, theta is a certain constant bigger than 1 over 2 mu. Okay. So essentially, we choose the step size to be a diminishing step size. If we choose such a step size, then we will have a very interesting convergence result. This convergence result says that the expected convergence error, this convergence error measures the square distance between xt and x star. And again, this is a random variable because xt is random. Okay, this entire algorithm is random. So we care about expected distance. Right. The expected value of this convergence error is bounded by some constant divided by t plus 1. Okay. Well, this constant is given as follows. So you can see this result is a convergent result. Basically, once you let t goes to infinity, you run this algorithm for a long time, this convergence error, this expected convergence error, will decay to 0. This expectation will goes to 0. Okay. And intuitively, this is because we are using a diminishing step size. Right? So following from the previous big picture, if you keep reducing the step size in a certain way, it is expected that the convergence error will also be reducing, okay? Will also be decreasing. So eventually, that's why we can get a convergent result in this case. Okay. So the conclusion is that we can get such a convergence rate. So it's roughly 1/t under such a diminishing step size. So the step size also decays with 1/t. And this is the complexity bound for SGD for the strongly convex case. And we will look at the proof of this result. So this is the proof. We are interested in such a distance, right? So this is this square distance between xt plus 1 and x star. Okay. And by the update rule, xt plus 1, by SGD update rule, xt plus 1 equals to xt minus the stochastic gradient. Right, just plug in the update rule. And then I can expand this entire term, the quadratic term, so I can expand it. We have xt minus x star squared. We have this term squared, and we have this intermediate cross term. Okay, product of these two. So it's just a quadratic expansion. And we do this because we want to relate the distance in t plus 1 to the distance in t, so that we can do telescoping later on. And here we need to, so if you look at these three terms, the first term is what we want. The first term is the distance in the previous iteration. We want to keep this one. The last term is the gradient norm of the stochastic gradient, the square norm of the stochastic gradient. And we can control this term. By assumption, we can control this term by using this assumption, right? So if we take expectation, then this assumption can allow us to control this term in the expectation sense. So therefore, we need to further deal with this inner product term, this cross term. And the way we deal with this term is to consider this expectation. Okay, so let's look at this inner product and consider the expectation. Okay, so I'm considering the expectation of this inner product. So to be more specific, here the expectation is taken with regard to say t. Okay, xt, we fix xt. So x star is a minimizer. Now we fix xt and take expectation with regard to say t. So this is okay. So and we can decompose into this double expectation using the iterate expectation law. Basically, the idea is this: in the inner expectation, for the inner expectation, we are taking expectation over psi t and conditioning on all the previous data samples. And this is equivalent to conditioning on xt, because the xt is generated based on the previous t minus 1 samples that we queried from SGD. So given Ksi1 to Kt minus 1, we can run SGD for t minus 1 iterations, and that will determine the variable xt. Right. So basically we are conditioning on xt. And the outer expectation is further taking expectation with regard to the randomness of this cosine 1 to cosine t minus 1. So then what happens next is that we will simplify this the inner conditional expectation. This inner conditional expectation, we have xt fixed because we are conditioning on these previous data samples. So xt is fixed. We take expectation only with regard to cosine t. Okay. Therefore, in this dot product, this is a constant. So therefore, we just need to take expectation with regard to the second term. And the expectation is with regard to cosine t. Okay. And we are conditioning on xt. And then the unbiasedness assumption tells us that given xt, the expected value of this stochastic gradient is exactly the full gradient, right, due to the unbiasedness assumption. So this expectation is exactly the full gradient at xt. So therefore, in the end, this term can be simplified. So this term can be simplified into this form. Is the expected value of the inner product between the difference of these two variables and the full gradient. So you can see in expectation, the stochastic gradient in this inner product can be replaced by full gradient. That's how we, like in the analysis, we use this unbiasedness property. By taking expectation, we use this unbiasedness property to get rid of this stochastic gradient. Because the stochastic gradient depends on which sample we pick. That is something that we do not know in general. Right? It's a random thing, but by taking expectation, we can get rid of the randomness. So it becomes full gradient. Okay. So this shows that for this inner product term, if we take expectation, we can get the simplified inner product. And the last term, as we just mentioned, by assumption, we know how to control the expectation of this term. Therefore, this motivates us to take expectation on both sides. Okay, so this 11.6, this equation, this is an equality, right? So the left-hand side equals to right-hand side based on the update rule. So because they are equal and because both the left-hand side and right-hand side are random, just involve some random stuff. So we can take expectation on both sides and still have this equality. And this is one step further. For this simplified inner product, we can say something about this inner product because the function f is assumed to be strongly convex. Right. So this inner product can be lower bounded by the distance by strong convexity. So this one by strong convexity, lower bounded by the distance as well. Therefore, by taking expectation, that simplified inner product, the expected value of the simplified inner product can be lower bounded by the expectation of this square distance. So basically, we take expectation on both sides. Right. Now, we take expectation on both sides of 11.6. Right. Left-hand side, we have the expectation of this distance. right-hand side, we have expectation of the distance in time t. For this inner product term, but we use this result to bound it. So eventually it is bounded by this this expected distance. Okay, and for the last term, once we take expectation, we use this assumption, right? The expectation of the third term, we use this assumption to control the last term. Okay. And here we assume CG equals to 0, so we don't have this gradient term. Okay, so we take expectation on both sides, plug in all these results, we can get this key inequality. It says that the expected distance in t plus 1 is less than equal to 1 minus 2 times mu times eta times the expected distance in t plus some small numbers. And here you can see that this coefficient is less than 1, so it looks like the distance is diminishing in a certain way. Like if we don't have this, if we don't have this term, then the distance is geometrically diminished. But we have this constant term. And for this coefficient, it comes from this one. Right? This part contributes the negative part of the distance. So it is critical. It is critical to have strong convexity here. Now the rest of the proof is an exercise. Basically, this is a recursion. Right, this is something related to t plus 1. This is something related to t. So you unroll this recursion, and we know the step size eta t is theta over t plus 1. So you unroll this recursion and do some calculations. In fact, you can use induction to easily prove the claim. So based on solving this recursion, we can get that convergence rate. Okay, we can get this convergence rate. So that's the idea. So in the convergence proof, the key step is to look at this one. So that's why in the analysis of stochastic gradient methods, people usually take expectation. Once we take expectation, we can get rid of this stochastic gradient. So it becomes the full gradient of the entire objective function, and then you can leverage. And now it becomes deterministic, sort of deterministic. Right? It does not involve these specific samples anymore. And this is a comparison between gradient descent and stochastic gradient descent for strongly convex problems. For strongly convex problems, we know that the iteration complexity is for gradient descent is log 1 over epsilon, because gradient descent for strongly convex problems, it has a geometric convergence rate. Okay, so that's why we have log 1 over epsilon, very fast convergence. However, on the other hand, in every iteration, we need to compute the full gradient. Let's say if your problem if your problem underlying stochastic programming problem has n data samples, that means in every iteration, if you want to apply gradient descent, you need to compute the gradient with regard to all these n data samples. So the per iteration cost scales linearly with your data size or the problem size. So the total computation cost is the multiplication of these two. You need to run this many iterations to achieve epsilon accuracy, and every iteration you need to compute the gradient with regard to n samples. So in general, your total computation of the gradient is n times log. But for SGD, the picture is very different. First of all, the iteration complexity, the convergence rate is much slower. It is just 1/t convergence rate. That means the iteration complexity is 1/epsilon. So this complexity is much bigger compared to the log 1/epsilon complexity. Because in this epsilon is a very small number, right? It means the corresponds to the desired optimization accuracy. So the complexity is much higher for SGD, but the benefit is that the per iteration cost is a constant. In the simplest case, every iteration you run, you simply pick one, you randomly sample one data sample from the data set or from the underlying distribution and compute the gradient with regard to only this data sample. So the per iteration cost is a constant, it's 1. Therefore, the total computation cost is over 1/, it's about 1/epsilon. So comparing this total computation cost, you can see that stochastic gradient descent does not scale with the data size. The total cost does not scale with the data size. So therefore, SGD is more appealing for problems with a large data size and moderate accuracy. Basically, if n is very big and your target accuracy is not that high, it's relatively small, then SGD has a clear advantage. So this is the case where SGD is more preferable over this gradient descent. So if you solve this, if you ignore this log part, okay, basically you need to compare n, the data size, with your target accuracy. Let's say if you are looking at a problem with 1 million data, and your target accuracy is only 0.01, which is not very high accuracy. Okay, then in this case, SGD is much better than the gradient descent. So, and this is really the case for most of the machine learning applications nowadays. You really have to deal with big data, but you are looking for a okay solution, not that high accuracy. And another appealing property for SGD is that the per iteration cost is very low. That means you don't have to load all the data in your GPU when you process this, when you do the optimization. So if you are training a neural network on a large data set, you can never compute the full gradient, because the computer most likely do not have a large memory to hold all the data. Okay, and next we can also talk about the convergence results of SGD without strong convexity. Right? So the previous result is about strongly convex problems. But what if we do not have strong convexity? So in this case, we consider the same problem setup, and the only difference is that we do not have strong convexity. We only have a convexity. Okay. So the previous proof does not apply anymore. This is because when we lose strong convexity, basically mu equals to 0. And the strong convex parameter equals to 0. And then this recursion is kind of a trivial recursion. If you unroll this recursion, then you will get a constant error in the convergence bound. So we have to think of another way to solve this problem. And this is the result for convex problems without strong convexity. Well, the left-hand side is, again, the expected optimality gap, the function value gap. But this x tilde t is not exactly the iterations generated by the algorithm, but rather here it is a weighted average of all the past iterations generated by the algorithm. Okay. And this weighted average, this coefficient, is defined by using the step sizes. Right? So it's a special weighted average scheme. And there's a reason that we need to use this weighted average. We will come back to this point later. But the left-hand side, you can view it as, okay. So now you can say that the output of the algorithm is such a weighted average. Okay? You look at this weighted average of the generated parameters as the output. And then for this particular output, we can characterize the convergence error as follows. So the convergence errors on the right-hand side is roughly, now this is a constant plus, this is a sum of the square of the step sizes, sum of the squares. Okay? And on the denominator is the sum of all the step sizes. Right, so you see that this convergence rate depends on how we pick this step size. Now, in particular, if we choose such a step size, 1 over square root of t, and once we choose this step size, we plug it into this convergence result, we can get this more explicit convergence rate. Okay. This convergence error is roughly log t over square root of t, and which can be is much smaller compared to the square root function. So we will first look at the proof of this theorem. Okay, so it is similar to the previous proof, but we have to do some modifications because now we do not have strong convexity. So we need to think of a way to leverage convexity in a more smartly. So remember that in the previous analysis, one key step is that we bound this inner product term in this form, right? And then the next, we leverage strong convexity. This is a key. We leverage strong convexity to lower bound this inner product term using the distance. Right? But now, once we do not have strong convexity, so this mu equals to 0, which means this lower bound is trivial. It's trivial in this case. So we need to consider bounding this inner product term using another strategy. So here we bound this inner product term using convexity. By convexity, we have this inequality, right? Convex functions satisfy this inequality. Therefore, if we take expectations on both sides and rearrange the terms, that implies that such an inner product term, right? The expectation of this inner product can be lower bounded by such a function value gap. Okay, so this is the only different from what we did in the strongly convex case. So we lower bound using this convexity. Now plug this new bound back into the previous proof, okay? And we will end up with this recursion. Okay. Now we have the function value gap that is caused by this bound, by this new bound. And then if you look at the right-hand side, you have difference of two consecutive distances. So we can do a telescoping, cancel them out. So we do a telescoping sum over k. Now these two cancels out. We only have the initial and the last term. Last one, we sum them up. Okay, so we have this one. And then we can further drop this negative term, because this is less than equal to. So we drop this one. Now we have this right-hand side. It's a constant plus sum of the squares of the step sizes. And then the rest of the step is basically to rewrite this inequality in a way so that, so first of all, we can, if you look at this one, first we divide both sides by sum of eta k. Okay. So divide both sides by sum of eta k. So the right-hand side is constant plus sum of squares divided by sum of eta k. Right? Now for the left-hand side, again, it's eta t divided, it is vk. Right? We go back to the previous one. Here we have eta k. And once you divide it by sum of eta k, so you have that vt. This is exactly eta divided by sum of the step size. So divide both sides by sum of the step size, and then this is a convex combination coefficient because they are positive, they are non-negative, they sum up to 1. Right? So by convexity, we can say that this part is a convex combination of all these function values. The convex combination of function values coming from the convex function. So by convexity, it can be lower bounded by the function value at that convex combination point. This x tilde is basically sum of vk times x tilde. Okay. That's exactly how we define this x tilde. The sum of, so this is vk, right? This coefficient is vk. We call it vk. So the sum of vk times x tilde, just by convexity. And this proves the final result. So this result, So when we lose this strong convexity, this convergence result can only talk about x to the t, which is the weighted sum of all the generated iterations. And turns out that this weighted sum is actually critical for many cases. Because if we do not do this weighted sum and only look at the last iteration generated by the algorithm, then this trajectory may be sometimes it is a random walk around that minimizer and never gets converged. It has certain variance. But by doing this weighted average, we can sort of cancel out reduce the variance and get a very accurate solution. And this is we can look at some examples to illustrate this idea. So the issue of SGD is that sometimes picking the step size is very critical. If you use a large step size, the iterations will never converge. Get a lot of randomness when you sample data samples. And the idea is basically to average the iterations. Okay. So you have x1, x2 to xt. So instead of looking at the last iteration, you look at the average of some of the iterations. That turns out to be more stable and usually can cancel out a lot of the noise. So it can mitigate oscillation and reduce the variance. So we have this example. So in SGD, if we look at this average iterates, right, so the average of all the previous generated iterations, then sometimes we can use a larger step size and improve the convergence. And I think we will see this in some of the homework examples. So numerically, you can compare these two strategies. One is to only consider the iterations generated by the SGD algorithm. The other is to consider taking the average of these iterations and then evaluate the performance. So for the rest of the time, let's look at the homework. Okay. Yeah, so this is about apply stochastic gradient descent to solve the least mean square problem in one of our previous homeworks. So the problem that we have seen this before, but this time I add some constant coefficients. So it's 1/2m ax minus b squared. It doesn't matter because I can just multiply by a constant, and the problem doesn't change the minimizer of the problem. But now the reason I introduced this factor is because this ax minus b squared can be written as this summation. Sum of ai, every row of a, sum of ai times x minus bi squared. And then this 1 over m will cancel this, will basically give us the average loss over this summation, right? Otherwise, as m goes to, if we have a lot of samples, the loss value may be very high. So normally we introduce this 1 over m factor to just to control the range of the objective value. And then this 1 over 2 is introduced because we have square. But once you take derivative, the 2 will cancel with 1 over 2. So it makes the derivative much simpler. Okay. So you can just adapt, update the problem that you constructed in homework 2. So here we are looking at the 1 over 2m times this least mean square loss. Okay, so what is SGD? So we are going to explore many different schemes associated with SGD, many hyperparameters and many different sampling schemes. So here we have m data points in total, right? When you construct this least mean square problem, you essentially generated m data points. For example, this m could be 1,000. You can do 10,000 if you like, because here, really the SGD can handle extreme scale problems. Now, so what we do, given an initialization, okay, this is standard. Given initialization, pick a proper learning rate and the proper batch size. So learning rate, we know about learning rate. It is the learning rate that we apply in the algorithm update. So what is this batch size? This batch size is a parameter that determines how many samples you query in every iteration from the data set. Okay, for example, in our slides, our batch size is only 1 when we introduce the SGD, right? Every iteration, you sample 1 data sample from the underlying data set or the underlying distribution. But in general, you can do a mini batch sampling. You can query a batch of samples. So this is called batch size. Okay, we usually choose 16, 34, 64, something like that. So normally these are 2 important hyperparameters: learning rate, batch size. Okay. So this is how we do the standard SVD. At every iteration k, we first randomly sample b data points from this data. In equation 1, you have m data points, like ai, bi, I from 1 to m. So you have m data points. So here in every iteration k, you first randomly query b data points from this data set. Okay, for example, you can query 16 data points. That is capital B equals to 16. And let's call this sample data points BK. This BK is a set of data points, collection of data points that you sampled in iteration K. And then this is the SGD update rule. So these are standard subtracts this is step size. Now this part gives the gradient of the loss function associated with that sample data points. All right, so because here we are looking at, so our objective function is this. Right? But in every iteration K, we sample BK data points, right? So that means in every iteration K, we are dealing with this. We are only dealing with this objective function instead of considering the average of all the data points. Right, this is the average. This is our original objective function. The average over all the data points. But in every iteration K, for SGD, we only deal with the average over a mini batch of data points. So this is the basic loss function for every iteration. So we take gradient with regard to this function. Okay? And by computing this gradient, we only need to access this small number of data points. Okay? So by taking the gradient, what is the gradient? The gradient is 1 over B just by taking the gradient. Right? Taking the gradient is quadratic. Taking gradient cancels out. We have AI. Right? This is a gradient. So this is what we see here. Right? That is, this is a, we call this the mini batch gradient. It's a gradient calculated over this mini batch data that you queried in every iteration. So you see, in every iteration, you are likely to query a different set of data. Okay? This BK, they are changing. It is changing over the iterations. So this is the SGD update. And then you have the following is a list of different SGD variants, different strategies that you can play in SGD. So let me explain the first one. Let's go over this one by one. Okay, so you pick a step size, you pick a batch size, for example, 16, right? You can implement this algorithm. Now in the first algorithm, we will do SGD with sampling with replacement. So what is sampling with replacement? That means in every iteration, so in every iteration, this mini batch of samples are randomly queried from the entire data set. So this is the most like the simplest way to do this data sampling, right? So every time I just query 16 data points from the entire data set. In MATLAB or PyTorch, you can use some random generators to get this. Okay? Say you have a 1,000 data points, and your batch size is 16. That means every time you will sample 16 points from out of these 1,000 points. So we call this sampling with replacement, meaning that every time once you sample these 16 points, you will put them back into the box. So next time again, you do this again, you will sample from this 1,000 data points. So in MATLAB and the PyTorch, you have a built-in function that allows you to randomly pick 16 numbers, different 16 numbers out of 1,000, for example, out of 1,000 numbers. Okay, so this is the first SVD algorithm. And once you implement this algorithm, you have this xk, right? X1, x2, x3 up to xk. and then you will report the loss value and the you will report the loss value of this at each xk. The second one is SGD with replacement plus model average rate. So it is based on the first one, you do a model average. Okay. Model averaging is like what we talked about in the slides. Instead of looking at these xk's, you look at their average. You look at the average of the xk's that you generate. Okay. So essentially, the algorithm is the same. The algorithm does not change, but you are only looking at different output. The third one is SGD sampling with replacement. This is exactly the same as before, right? And the only thing different is the momentum. Okay. You can inject momentum to this update. Okay. Remember, we talked about the momentum for gradient descent, right? Here, the idea is exactly the same. The only difference is that here we are using stochastic gradient instead of the gradient, full gradient. But you can simply follow the previous accelerated algorithms, follow that scheme, and inject some momentum to this SGD update, and see if momentum can accelerate the stochastic gradient descent algorithms. And of course, when you inject momentum, we have the momentum coefficient. So you will also need to tune another hyperparameter. Okay. So I think we can first focus on the first three SGD algorithms, and we'll talk about the rest of the SGD algorithms maybe next time. So the first one is standard SGD, but we do mini batch sampling. Right? Every time we query 16, 32, 64 samples from the data set, you will need to pick a proper batch size. And the second one is the model average. Okay. And the third one is injecting momentum. And for these algorithms, we will just report. I think this is similar to what we have done before, just the y-axis is always the objective function value, but now the x-axis is different. Okay. It is the number of data points used. The number of data points used. Because previously, when we talk about when we do the experiments, the x-axis is always the number of iterations. Because for example, for gradient descent methods, really the computation complexity is only scaling with the number of iterations. But for SGD, because of this batch size issue, we can no longer use that metric. Okay. For example, if you run gradient descent for one iteration, you will need to access to all the data points you have. If you run one iteration as a gradient descent, you need to access all the data points. But if you run SGD for one iteration, you only need to access these B data points, right? So it's much smaller. So it is not a fair comparison. So here we will just use this normalized metric, the number of data points that you sampled as the x-axis. So the computation complexity will proportional to this number. Okay, so it's a fair comparison between different among different methods. Yeah. So specifically, every iteration of SGD algorithms consume B data points, while every iteration of gradient descent consumes M data points. So they are not directly comparable. So we have to consider the total number of data points used. This is a fair comparison between different methods. So simulation 2 is try different batch size and learning rates, but we can talk about this later. Okay, so it's just once you set up simulation once, second one should be very simple. Okay, so I think this is everything for the SGD. So next time we will talk about I think it's variance reduction methods. Yeah, so these are more advanced variants of the SGD algorithm. Okay, I will see you guys next Tuesday.
Well, thank you for class.
Yep. So if you have questions, just let me know. I think the homework A will take a little bit time to set up. Okay, see you guys.
All right, see ya.